So today we're going to be talking about electrochemical cells, and electrochemical cells are also called galvanic cells or voltaic cells. They're named after the scientists Luigi Galvani and Alessandro Volta, respectively. They're electrochemical cells in which an electric current is generated from spontaneous oxidation reduction reactions. And as you can see here, the galvanic cell consists of two different metals. This first electrode here is the zinc electrode, and we have the copper electrode. The zinc electrode is placed in a solution of zinc solution, so it's like zinc chloride, zinc sulfate, zinc whatever. And copper, also copper chloride, copper sulfate, copper nitrate, whatever you want it to be. It doesn't really matter. But what's happening is that we have this salt bridge here that is connecting the two containers. It allows the electrons to flow from one beaker to the other beaker. It's going to be your job to figure out which direction the electrons flow. Now, it's in a closed system here, a closed circuit, and because it's in a closed circuit, it can take a voltmeter reading. It can tell you how many volts this battery will actually produce. So in order to figure out or to believe that the electrons are moving from the zinc over here to copper as the arrows show, we have to be able to write half reactions for them. So, and we're also going to have to use a table, and let me grab that for you. Here is the table. This list of standard reduction potential for half reactions is a standardized value. They've all been tested, put on a chart, and it's your job to be able to gather the information. We can see that each half reaction predicts how many volts will be produced. And so what we do find out is there's a trend on how to use this, and I'll show you what that is in just a second. But we want to find zinc 2 positive, because here my picture shows zinc 2 positive going to zinc. So I find zinc 2 positive going to zinc. Right there it is. And I can see in this reduction, this half reaction reduction value, that the voltage is a negative 0.76 volts. And then I go and I look for my other guy, which is copper and the copper 2 positive, and I see it's down here a little bit. Here's my copper 2 positive plus my 2 electrons producing copper, and that has a positive 0.3 volts. Now, both of these half reactions are reduction reactions, but we know in redox one has to be an oxidation and one has to be reduction. So we have to flip one of these two half reactions. Well, the way you choose it is you want to flip it so that the voltage here, if I flip the zinc reaction, the voltage then has to become a positive 0.76 volts. And that would leave my copper equation at a positive 0.3 volts. So when I add those two values together, I get an overall positive voltage. Now, if I had chosen to leave this guy as a negative 0.76 volts, and I flipped this guy, that would give me a negative 0.3 volts, and I would get a negative voltage, and there's no way for that reaction to be spontaneous, so I chose wrong in that case. So here's the other trick. The higher on the list, the more likely it's going to flip. It's not, if it's higher on the list, it's not going to be a reduction reaction, it's going to be an oxidation reaction. So because zinc's higher on the list, I'm going to be able to flip it, and I'm going to be able to say that I have a positive 0.76 volts. And on my paper, I'm going to show you here, look at that, that says zinc now will produce zinc ions plus 2 electrons. And you can see I wrote zinc plus zinc ions plus 2 electrons, and I'm writing it as a 0.76 volts. Now you can see I listed it as oxidation because I'm losing those 2 electrons. I recorded the copper equation exactly as I saw it on the paper, and I wrote down the positive 0.34 volts. And you can see that it gained 2 electrons, so it's reduction. Awesome. Now, that means if zinc is oxidizing, it's losing electrons, it means that the electrons are flowing away from it and going to copper. Now, in a battery, we have 2 ends. We have an end called the anode and the cathode, the positive end of the battery and the negative end of the battery. The easiest way to remember this, if something is undergoing oxidation, it starts with the letter O, it's a vowel. Anode starts with the letter A, also a vowel. Oxidation is the anode end of the battery. And we know that the anode end of a battery is the negative end of the battery. So here we say this is the anode, and we see it's at the negative post. The cathode, which is the positive end of the battery, goes with reduction because they both start with consonants. You have R and you have C. They go together. Now the total voltage that we would have here for this is by adding these 2 volts together to get 1.1 volt. Okay? So what I'm asking you to do on the blue sheet, go down here, is doing something very similar. Can you draw and label a diagram, this time for aluminum and lead? So I made you a little sketch for my aluminum and lead, and I had to figure out which direction, as the first thing says, is which is more easily oxidized, aluminum or lead. So I had to find my 2 half reactions, and I came over here to my blue sheet and I scrolled down and I found aluminum, and I scrolled down and I found the lead. Well, typically because aluminum's higher on the list, this is the one we're going to flip. And let's just check it. If I don't flip it, aluminum's a negative 1.66. If I flip this one, it's a positive 0.13. That's not going to work. So higher on the list, I flipped it and I made it a 1.66 volts. And you can see that over here, I flipped that half reaction. I wrote it as 1.66 volts. I copied down the lead reaction and negative 0.13 volts. And I will add those 2 volts together to get my total expected voltage that it could produce. I then completed my half reactions. My electrons lost did not equal my electrons gained, so I multiplied and distributed and got my reaction. Okay. So then it says here on the paper, which is more easily oxidized? You would say aluminum. Write the balanced redox reaction using the 2 half reaction method, which we did right here. What is the maximum voltage that the cell can produce? I added those 2 volts together to get a positive. It has to be a positive voltage, otherwise it's not going to be spontaneous. Okay. What is the direction of the electron flow? It is always going to be the oxidized to reduction. So aluminum was oxidized, so the electrons are going to pass through, okay, over to lead. Question, which electrode is decreasing in size? Okay, so if I am decreasing in size, that means, if I look at my picture here, if we look at this formula, aluminum was elemental and it's becoming an ion. So it is decreasing in size, whereas the lead ion is going into lead, so that means that lead is increasing in size. The anode is where oxidation occurs. So anode, we said the anode was oxidation. Aluminum's undergoing oxidation, so it's anode. It is the negative post. And then because lead was undergoing reduction, that means it's the cathode, and it is the positive post. Number 10 and 11 already took care of that. Number 12, when the reaction reaches equilibrium, what is the voltage of the cell? That means your battery died. And when your battery dies, you have 0 volts. So after we do a little bit of that, I'm then going to give them this white handout here called Diagramming Galvanic Cells. The vocabulary of cathode, anode, voltmeter, wires. We're going to work with those in the lab. 2 half cells, ion movement, direction of flow, salt bridge, overall reaction, and line notation. The line notation is talking about down here, but how do we write our final answer? So if you notice, it went from SN to SN2 positive. Okay, that is where my oxidation is occurring. Remember here, if we look at this picture, it was going from Al to Al3 positive. That's where oxidation occurs. So I am showing here, this is my oxidation, this is my anode end, And you can see I went from 2 positive to copper, and just like here on lead, it went from the 2 positive to lead. That's my reduction end. That's where my cathode end would be. So basically it's my anode, then my cathode. Okay? Just giving you some helpful hints on how to write it. So we have a couple of practice problems front and back. We'll make sure you're okay when you get back, and good luck at Quiz Bowl.